Hello and welcome. I am Khalid Gamish. I'm proud to present my bachelor's degree project from the University of Tripoli, Faculty of Engineering, Department of Mechanical and Industrial Engineering. The project is entitled Simulation of RS-25 Engine using Flownex software. The contents. First, we will begin with introduction. We will talk about cryogenic engines, what they do and how they work. Then we will navigate through the equations that used to complete the simulation. Moving forward, we will dig into the RS-25 engine, covering specifications, operational conditions, and we are going to build a deep understanding of the mechanical components and how they work. Next, we will take a glance at the software we utilized for the simulation, Flownex. We will provide a brief overview of its capabilities and how it contributed to our project. After that, we will go through a case study, breaking down how we did the simulation step by step. Finally, in the results and conclusion segments, we will present the outcomes derived from the simulation, compare them with the actual data, and discuss them. So, let's begin. Let's talk about cryogenic engines. These are special type rocket engine that relies on cryogenic fuels, which are gases or liquids that have been cooled to extremely low temperatures. The term cryogenic refers to the very low temperatures at which these fuels are stored and used, typically below -150 Celsius. These engines are used in a variety of space missions and satellite launches. In order to understand this complex engine, we need to start from the fundamentals. The rocket propels itself high into the sky using Newton's third law. This occurs by releasing a large amount of gases at high speed. The greater the quantity and speed of the gases, the greater the thrust that produced. For any combustion process to occur, we require both fuel and oxidizer. While most vehicles carry fuel in tanks, for space travel we also need to carry oxidizer along. The fuel and oxidizer together are called propellant. Filling tanks with gaseous fuel and oxidizer requires large tanks, which in turn will increase the rocket's mass and making takeoff difficult. The solution is to cool the fuel and oxidizer to extremely low temperatures, turning them into liquids. In cryogenic engines, we face two main challenges. Firstly, in the main combustion chamber, the temperatures can reach up to 3300 degrees Celsius, which could instantly melt the nozzle walls. Secondly, as mentioned earlier, the fuel and oxidizer are kept at very low temperatures. Therefore, they need a lot of energy to raise their temperature. To solve this problem, the cold propellant is passed through tubes or channels in the walls of the nozzle and combustion chamber, where it absorbs heat from the hot gases. Like any other engine, cryogenic engine needs a pump to propel the fuel and oxidizer to the combustion chamber. What about an electric pump? An electric pump would require a lot of energy storage, which add more weight to the rocket. A clever solution is to run the pump using a turbine which operates on expanded fuel. The turbine pump arrangement is called turbopump. In our case, the expanded fuel is not enough to rotate the pump at high speeds. So we add a preburner to burn a part of fuel and use its exhaust to drive the turbine. Type of cycles. Here we see the flow diagram of the simplest cycle known as the open cycle. As we know previously, propellant is pumped into the main combustion chamber by the impeller. In this cycle, a small portion of the fuel and oxidizer is directed to the preburner. where it ignites, and the resulting exhaust drives the turbine. The majority of the fuel and oxidizer continue to the main combustion chamber, where they are burned. The exhaust gases are then accelerated by the conversion-diversion nozzle. This cycle is considered to be the simplest, but also the least efficient. This is because a significant amount of energy is lost in form of the hot exhaust gases. These energy losses spurred the development of more complex cycle. The other types of cycles are known as the closed cycles. We have three types of closed cycles. Closed cycle oxidizer rich, closed cycle fuel rich, which will be the subject of our study, full flow staged combustion cycle. The objectives. The cryogenic engines play a key role in the space industry, which will have significant impact on overall development of human success. The cryogenic engines are the most complex rocket engine technology in terms of design and operation. And when all complexities of the rocket engine designs are taken into consideration, 3D CFD analysis on system scale is not a available option. So, the best option is to use one-dimensional CFD softwares to simulate the whole system. In our study, we will use the Flownex simulation environment to simulate the RS-25 engine, the most efficient rocket engine was ever built. The RS-25 engine was used as the main engine of the Space Shuttle, and now is the main engine for Space Launch System, which plan to use in Artemis project. And we will compare the results of our simulation with the results provided by the manufacturing company to see how the engine reacts in different conditions, both in steady state and transient. Basic laws and equations. First, we will begin with specific impulse equation. Specific impulse is a measure of rocket engine's efficiency, and it's equal to the thrust produced by the engine divided by the mass flow rate of propellant times gravitational acceleration. Ideal gas law was used mainly to calculate the density of air at different altitudes. The thrust equation. Sound velocity equation was used for the calculation of the Mach number. The Mach number is a dimensionless quantity that's used to describe the speed of an object relative to the speed of sound. Nusselt number is also a dimensionless number and was used for the calculation of heat transfer coefficient. Heat transfer coefficient equation. This equation is used to calculate the temperature of atmospheric air at different altitudes. And finally, the equations that used to calculate the atmospheric pressure at different altitudes. The RS-25 engine. RS-25 was designed and manufactured in the USA by Rocketdyne. RS-25 operates on a fuel-rich staged combustion cycle that burns cryogenic liquid hydrogen and liquid oxygen. RS-25 specifications. RS-25 operates on a fuel-rich cycle with two preburners that drive the high-pressure turbopump. The RS-25 engine burns liquid hydrogen and liquid oxygen propellants, which known of their high specific impulse, with mixture ratio of 6 to 1. The RS-25 engine stands out for its variable thrust capability, allowing it to adjust thrust levels during different phases of flight. This is achieved through a throttling process to control the flow of propellants. Throttling is accomplished by varying the output of the preburners, thus varying the speed of the high-pressure turbopumps and therefore propellant mass flow rates. The RS-25 engine is the most efficient engine was ever built, with a specific impulse approach 452 seconds, and utilized a two-stage combustion process with efficiency of 99.6%. The main combustion chamber pressure reached 3008 psi at full power level. Also, the RS-25 engine features a remarkable high expansion ratio of 69 to 1 between its nozzle exit area and throat area. Here we present the main parameters of the nozzle and combustion chamber. Here we will show the main components of the RS-25 engine. The low pressure oxidizer turbopump. The low pressure fuel turbopump. The high pressure oxidizer turbopump. The high pressure fuel turbopump. The oxidizer preburner consists of 120 coaxial injection elements, while the fuel preburner injectors consist of 264 coaxial injection elements. The main injector is composed of 600 coaxial injectors that inject the propellant to the main combustion chamber, where the propellant burns at 6000 degrees Fahrenheit, and the resulting exhaust gases flow to the nozzle, where the velocity of the gases increases significantly to produce high thrust. The software used for the simulation, Flownex. Flownex simulation environment. Flownex software determines pressure drop and heat transfer for the connecting components of the complete system in steady state and transient. Flownex has the ability to simulate simple subsystems up to complete systems. Anything from ventilation and reticulation networks, detail internal turbomachinery flows, up to boilers and complete power generation cycles, like Rankine and Brayton cycle. Flownex has the ability to simulate integrated flow, heat transfer, mechanical, and Flownex control systems, give you a complete system response. This include liquids, gas, two-phase, and mixtures. Integration with other software allows further integrated simulation. This include Fluent, ANSYS, MATLAB Simulink, LabVIEW, Excel, MathCAD, and OPC. Flownex includes standard models and components for all the equipment in typical fluid thermal systems. This allows you to quickly configure the system. And now let's go through the case study. First, we will start by analyzing the flow of propellants to understand how the engine works. Next, we will delve into the simulation process and show you the steps involved in creating a virtual model of the engine. And then we'll present the components that used in the simulation. Finally, we'll provide an overview of the script developed to simulate the kinetic properties of the rocket. And here we see the flow diagram of the RS-25. Here, the liquid oxygen entering at the low pressure oxidizer turbo pump. From there, it passes through the low pressure oxidizer duct and to the high pressure oxidizer turbo pump, before splitting into a main flow and several branches. The majority of the oxidizer continues into the main combustion chamber. One branch supplies liquid oxygen back to drive the low pressure oxidizer turbo pump turbine. The turbine discharge flow then merges with the pump output flow, which goes again into the high pressure oxidizer turbo pump. The remaining oxidizer supplies the pre-burners, which pumped at the bottom of the high pressure oxidizer turbo pump, allowing it to be injected into the pre-burners. The fuel flow process begins when liquid hydrogen enters the low pressure fuel turbo pump and flows through the low pressure fuel duct to the high pressure fuel turbo pump and main fuel valve. Up to this point, the fuel system is insulated. After passing through the main fuel valve, the hydrogen is allowed to warm and gasify as it enters the diffuser, where the flow splits into three paths. This path goes to the main combustion chamber coolant channels, where it absorbs heat to cool the combustion chamber walls, then drive the low pressure fuel turbo pump turbine. The other path passes through the 1080 nozzle tubes and joins the third path, which bypasses the nozzle through the chamber coolant valve. The combined flow then splits to feed the pre-burners. Then the mixture is burned to run the turbines of high pressure turbo pumps, then flow to the main injector and injected to the main combustion chamber. To begin modeling process, we start at the inlet of the hydrogen and oxygen. Then model the components one at a time, solving the model as we progress. The components that used in the simulation. We have also developed a script to calculate the kinematic properties of SLS during its flight. This script uses the equations of motion to calculate the velocity, acceleration, and position of the SLS as it ascends through the atmosphere. Some simplifications have been placed in this study, as the primary focus was on investigating the performance of the engine under various conditions, rather than analyzing the specific flight trajectory and path. The free body force diagram of wingless rocket can be simplified as follows. We assume that the flight trajectory is vertical, so the angle of the flight path is 90 degrees. Also, we assume that the external forces such as wind, thrust misalignment, and solar attraction are negligible. So when we apply Newton's second law, we got this. And this is the final result of the full network. So let's take a look at it. Here we see the low pressure fuel turbo pump created by pump, shaft, and turbine components. The valve components are used to simulate engine different valves. Here we use simple PID controller to control the opening of the chamber coolant valve. We see here the oxidizer side and the nozzle side. Here we see the power level track bar that changes the valve level to change the thrust of the engine from full power level to minimum power level. And here we have the script component that used to calculate the kinetic properties. Here in inputs we can enter the drag coefficient, the booster thrust, number of engines, mass of the vehicle, vehicle cross-sectional area, booster mass, and booster cross-sectional area. As we see here, we have the variables list, the code, and now let us solve it in steady state and run it transiently. Here we see the atmospheric pressure decreases as the vehicle takes off and the altitude also increases. Here we see the speed chart of turbopump shaft. We see that the speed changes as it's seeking equilibrium. The atmospheric pressure kept decreasing. Let's change the power level of the engine and run it in minimum power level. We see the speed of turbopumps immediately goes down and thrust decreases. Let's increase it to full power level. As we see the turbopump speed begin to increase and also the thrust. So this is the final network. Results and conclusion. Here we see the results from solving simulation in steady state. We have simulation values, actual values, and error percentage of thrust at nominal power level, specific impulse, chamber pressure at nominal power level, oxidizer mass flow rate, and fuel mass flow rate. Here we have the results of the transient data. We have the thrust at different power levels. We see here the thrust to high chart. The conclusion. As we see, the results obtained from the simulation closely aligned with the actual data, with an acceptable percentage error. This due to the simplifications that were applied to the system. But it still gives us a valuable information about how the engine works under different conditions. The thrust versus height chart shows that the thrust varies greatly in the first 20 kilometers. This due to the fact that the atmospheric pressure decreases rapidly with altitude in this region. As altitude increases, the atmospheric pressure decreases more slowly and the thrust will vary slower as a result. And this leads us to the fact that the Flownex is a great software for simulating rockets, because it's able to model the different parts of rocket engine in great detail. This includes the combustion chamber, the nozzle, and the turbo machinery. Flownex is relatively easy to use, making it a great choice for both experienced and novice rocketeers. Optimization for each component. As we know, Flownex has the ability to integrate the results with other softwares, so you can improve the accuracy of the simulation by simulating and designing the pumps and the turbines, by coupling the information you get into ANSYS software and make 3D design to the component independently to get more accurate estimation of the flow rate and pressure. More precise data. If you can get more precise information from the company, such as the exact diameters and the materials of the pumps charts will also help to improve the accuracy of the simulation. The boosters are an important part of the rocket, so it's important to simulate them. Simulation of the actual path. This is more advanced simulation, but it can be very helpful in understanding how the rocket will behave in flight. By simulating the actual path of the rocket, you can get a better estimate of the thrust and drag forces, which will help you to predict the flight trajectory. Using Flownex in subjects. Flownex is a powerful tool that can be used to teach a variety of subjects related to fluid mechanics and thermodynamics and heat transfer. And by simulate different cycles like Rankine cycle and Brayton cycle, also fluid networks, you can help students to develop the skills they need to succeed in these fields. Thank you for watching. If you need to know more detailed information about the project and simulation, I'll be happy to share it. Just send it in the email. And thank you.